All right, we finally get to section 15.4, and we're going to break this up actually into two different presentations. The first one, this is all about titrations. The first one here, part one, we'll do strong acid-base titrations, and then we'll move on to weak acid-base titrations. This is just some of the vocab you need to know for our titration, and we've talked a lot about this. The titrant is what we have in the burette. That's what we are titrating with. Indicators change colors at endpoints. We know how to read titration curves. And really just a reminder here between endpoint and equivalence point. Equivalence point is a mathematical thing where the moles of acid and base are equal. Endpoint is a visual thing where the color change happens. That color change happens over a very wide range. The equivalence point is just one little point in that, and we want to try to make sure those are as close as possible. And then we will talk about the midpoints, where pHs or pKa's. That's more for weak acids. We talk about midpoints of titrations are really important for buffers. So here's our strong acid-base problem. It says a 50 milliliter portion of 0.15 molar NaOH is titrated with HCl. Calculate the pH when the following amounts of HCl have been added. Whenever we have volume changes, we need to do everything in moles and dilute our molarities into their final molarities. But for for part A here, there is no volume change. Initially, no acid has been added. So in part A, we simply say our initial solution is just sodium hydroxide. So the negative log of my 0.15 molar sodium hydroxide gives me a POH. That POH is going to be 0.824, and my pH for part A is going to be 13.18. Okay. So part A is actually pretty easy here. Strong acids and bases, we just take the concentration of whatever we have at the end. But if we didn't add any acid, there's no volume changes, we don't really care about that 50 milliliters, we just take the molarity, negative log of the 0.15. Part B, now we have some volume changes. So for part B, we need to worry about our actual reaction. Now we're adding the acid, and we have hydroxide turning into water. This is a neutralization, okay? So this will be a limiting reactant problem because acids and bases react with one another almost 100%. And since there are volume changes, everything is going to be in moles. So my acid, we have 5 milliliters of 0.25 molar acid. So that's going to give me a 0.00125 moles of acid. The base is, now we've got 50 milliliters of 0.15, so 0.0075 moles. We will never really worry about the water because it's a liquid and it's the solvent. 1-to-1 ratio, the acid is going away to 0. So that's all gone. My base is going away, minus 0.00125, and we'll be left with 0.00625 moles of base. And now I've got 55 milliliters of solution. So divided by 0.055 liters, that's going to give me 0.114 molar hydroxide. So we just classify everything, and this is going to be way more important for weak acids and bases. But what is this thing that is excess? It is a strong base. So we're just kind of back to where we were with A. I've got a lower concentration now than I did before because I neutralized some of it. But this is just take the negative log of my new molarity, 0.114, and we get 0.944, which is a POH. Therefore, my pH is 14 minus that, 13.06. So we only added 5 milliliters of the acid, which is not a whole lot, but we neutralized just a little bit of the base. You can see the pH went down a little bit, but not a significant amount. Okay, so I have excess hydroxide, so then we just solve a strong base problem at the end, negative log of my strong base. Same problem, part 3 then, let's reset, says if we had 30 milliliters of acid. So let's do this again. We want our H plus and our OH minus, making H2O. This is part C. This is again a neutralization, which means we want a limiting reactant problem, not equilibrium. So we got BCA. And now our volumes here, we always kind of go back to the beginning. Sodium hydroxide, 50 milliliters of 0.15 molar, kind of starting from scratch is 0.0075. And now we've got 30 milliliters of 0.25 molar acid, which also is 0.0075. Now, strong acid-base problems here, these are really nice. We don't really care about the water. This is a 1-to-1 ratio. They're both gone. So those are both 0. So what do we have at the end? Well, we only have water. I don't have any hydroxide or any hydrogen, and there's just water on the product side. So what is the pH? Well, the pH is just 7, because strong acids and bases have their equivalence point at 7. So this is the equivalence point. And then just recognizing titration curves for strong acids and bases. Here we have a low pH, so this is an acid being titrated with a base. We get our S curve here. It's a limiting reactant. My acid is being neutralized slowly but surely. And then there's a big spike when it starts to change rapidly. Our equivalence point is always at 7, and now I have excess hydroxide on the tail end. And we can look at that the other way. If we had a base neutralized with a strong acid. Now I'm starting with a high pH. I have a base and I'm titrating it with an acid instead. This should say milliliters of acid added here at the bottom. That's a typo. Let's cross that out. And how do you, just by looking at this curve, we know that this is a strong acid-base problem because the equivalence point is right at 7. Weak acids and bases won't do this. This is, I'm starting with a base, I'm titrating with an acid, and they're both strong because my equivalence point is at 7. Those are the important features we want to recognize for titration curves, especially for strong acid-base problems. And then we will do weak acid-base titrations in part 2.